All right, Math 6610. A lot going on in this video. Well, actually, I'm not sure if I'll get it all covered or not. I may have to break it up into multiple videos. But anyway, going to talk about type 1, type 2 errors, power, effect size. And I want to do a demonstration of how power is actually calculated, and type 1, type 2 errors. So anyway, let's go through some just some definitions. Type 1 error is the probability of rejecting a true null, and it's denoted by alpha. Type 2 error is denoted by beta, and it's the probability of failing to reject a false null. Now, I think the easiest way to remember this is to look at the contingency table. And so if we think about the statement for H sub O, this is either true or false, right? Problem is, in hypothesis testing, inference in general, we never know whether it's true or false, but in theory, this statement is a true statement or it's a false statement. Now, the decision, be really good if you could see that, right? And trust me, I can spell, I just can't write, D-E-C-I-S-I-O-N. Anyway, decision is either reject H sub O or fail to reject H sub O. Now, let's just think it through in the simplest terms. If H sub O is false, then we hope that we reject it because we don't want false statements staying on record. So I'm going to put a big old smiley face there because that's when the process worked. If H sub O is true, then we hope that we failed to reject it. Again, smiley face, because that means that our inference process has worked, right? We want to keep true statements around, so we don't want to reject those, and we want to reject false statements. Again, that's when the process works. Now, when do we know that? Well, we don't, because again, we're dealing with this all in theory. Well, these two boxes here provide issues. And this issue, if we reject a true null, I'm going to put a 1 there and a 2 there because this is the definition of a type 1 error. This is the definition of a type 2 error. In this little box, I'm going to put alpha. In this little box, I'm going to put beta for obvious reasons. It's the way we define the two errors. Now, once we have these errors defined, we can talk extend this a little bit into some other ideas. Number one, power. Power is important in designing a study because we kind of want to find a balance point to where we find adequate power, and desired power is typically 0.8. By definition, power is the probability of rejecting a false null. And if you think about it, that's the motivation of any study, right? We have a concern about something on record. We want to challenge it. So that's kind of the status quo or our null hypothesis, and we always kind of hope that we reject it. Now, we're not going to do anything unethical to create statistical significance, but that's typically the hope when you design a study. Now, so we can extend this beta, which is again the probability of a type 2 error, to 1 minus beta, which is the power of our test. Now, if we don't get enough power, let's say we do a priori power analysis, which I'll demonstrate to you in later videos, and we come up with a power that's significantly or quite a bit less than 0.80, then there could be a false null lurking around, but we don't have enough statistical power to identify it, to reject that statement. If we get too much power, then we're going to reject everything, leading to statistical significance, but not practical significance. Now, let me tell you what can happen there. Let's say that we feel that the mean ACT at a very large school district is 23. And we're going to test that against mu not equal to 23. And let's just say that we identify our probability of a type 1 error at 0.05, our alpha value at 0.05. Now, if we would get a power, let's just 99.9%. This says that we have a 0.9999. Okay. 0.999 probability of rejecting this statement if it's false, which pretty much tells us we're going to reject this statement pretty much exhaustively. But let's say that the mean actually turns out to be, the true mean is 23.01. Well, that difference of only 0.01 is going to be identified by extreme power. So we're going to get statistical significance because, again, mu is not equal to 23. It's equal to 23.01. But in terms of practical, we're going to get statistical significance. But in terms of practical significance, is there really a difference between 23 and 23.01? Yeah, I would argue that there's really not. Once we talk about power, again, we want to find this kind of perfect balance, and most people say that's 0.80. Again, too much power, we get statistical significance, but lacking practical significance, and not enough power, we don't have the statistical, I guess, potential to identify a false null and reject it. Effect size is something else that we need to learn about, and I defined it as an objective or standardized measure of the magnitude of a difference. Now, keep in mind that we can reject anything if our sample size is large enough. So, for example, let's say that we have a test statistic that deals with the z distribution. And let's just say that, well, let's just think about it in theory. If I increase this, what happens? Well, by increasing the denominator of the denominator, I'm going to make this a smaller number, making my entire statistic larger. Well, we know from previous videos that as our test statistic gets larger, our p-value goes down. So we can hold this, and this constant. And just by increasing our sample size, we're going to increase our test statistic, which is going to decrease our p-value, leading to statistical significance. Well, statisticians noticed this a few years ago, and they came up with a standardized, I guess Cohen was the main man in this, but to come up with an objective or standardized measure. So again, effect size is control that a sample size large enough will always lead to statistical significance. And another caveat or advantage to this is that effect sizes being standardized, we can compare across different studies. All right, let's talk a little bit about calculating power, and I think this really is a good illustration, even though it's not realistic. Okay, when we conduct, well, let me just play it out, and I'll point out the issues as we go along. So let's say, for example, that We are testing that a claim that a population mean is equal to 100 against or versus population mean not equal to 100. We're testing at 0.05, so what we can think right off the bat, this is a probability of a type 1 error. Because again, alpha is the probability of a type 1 error. So we are allowing ourselves a 5% chance of creating this error. So we know from the central limit theorem and sampling distributions that this distribution would be centered around the claim. The population standard deviation is equal to 15, telling me that the standard error of the sampling distribution will be equal to sigma over the square root of n. So this is going to be 15 over, and let's just say that our sample size is equal to 25. So just as an example, since we know that our standard error is equal to 3, that approximately 68% of the samples are going to be between 97 and 103. And about 95% of our samples are going to be between 94 and 106. Now, we can take this a step further, and we can find, since we're testing at 0.05, we can find the values that have 0.025 in this region and 0.025 in this region. Turns out it's very, very easy to do, right? We need to find the sample mean. Actually, we need to find two of them that separates the fail to reject region and the reject region. All right, so that's going to be easy to do because we know that the z-value comes in this form. We know from previous videos that the z-value that separates the top 2.5% with the bottom 97.5% is 1.96. We've seen that before in videos. So I know that my z-value here has to be 1.96. I don't know the sample mean that corresponds to that. That's what I'm trying to solve for. We know that we're living in a distribution with a mean of 100, and we know that we have 15 over the square root of 25. So 1.96 equals x bar minus 100. I believe this is what, equal to 3. So we can put that very quickly into our calculator. And it looks like to me that this x bar is going to be 105.88. Don't you wish it would stay this easy? Now let's just go ahead very quickly and calculate this. It's going to be very easy because the only thing we would do there is come in and do negative 1.96. And we get 94.12. Now, what's the significance of these two values? This tells us that if, again, go back to the assumptions here of a type 1 error, if H sub O is true and we reject it, then we've committed this type of error. In the context of this example, if this is a true statement, and we get a sample mean that's greater than 105.88, what decision are we going to make? Well, we're going to make a decision of reject. Or if we get a sample mean of 94.12 or less, what decision are we going to make? We're going to reject a true null. So this region down here and this region right here is essentially just alpha, which is the probability of a type 1 error. 2.5%, 2.5%, 0.025, 0.025 adds up, of course, to our alpha value. Now, let's take this a step further and talk a little bit about power. Now, the caveat to power is we have to make some assumptions here. To calculate power, we see that it's a function of beta. And beta is what? Beta is the probability of a type 2. The definition of a type 2 is H sub O is false and we fail to reject it. So what we have to assume here is kind of strange, but since it's false, to calculate power, we have to calculate power based on another mean. So again, we've got our initial distribution, with a mean of 100 because that's what's hypothesized. But let's say, for example, that the true mean is equal to 105. Now, let me pump the brakes a little bit and be completely transparent with you here. I'm going to demonstrate something to you that would never be done in research. Why? Because we never know if this is true or false. And if it is, somehow we have some inside information that it is false, we never really know what it is. We can estimate this using a confidence interval, but we never know. So the calculation of the power using this approach is really meaningless in education research. But it provides a really nice illustration of what's going on with power and type 1 and type 1 and type 2 errors. Okay, so let's think about what we've got. We found out before that 105.88 played a pretty key role, right? So this is a sample mean. And of course, the X bar down here, 94.12, played a critical role because, again, it separates the decision, right? It's the decision criteria. But with respect to this problem, knowing that, again, in an attempt to illustrate power and the probability of a type 2, knowing that the mean isn't 100, it's something else, and we're just making the assumption it's 105. What happens with these errors? Well, again, it turns out that this right here would be the probability of a type 1, right? Again, this is true. If we get a sample mean down here, we're going to reject a true null, so we've committed a type 1. Now, switching gears completely, our focus turns to mu equal 105 because we're talking about the context of beta, the probability of a type. So I want you to think about, now we're residing in this distribution, so all of our calculations have to take part in that distribution. So I want you to think about, what does this area. Sorry. And again, let me repeat what I just said before. All of our calculations now have to take place in this area, right? That may be the ugliest shading of a distribution I've ever seen, but pretend it's pretty. So what does that area represent? Well, what happens? If we get any sample mean over here, what is going to happen? We're going to reject the claim of 100 when we should have, because the mean isn't 100, it's 105 in this illustration. So this part right here actually turns out to be the power of our test. I wish I had another. What happens in this area? Again, this goes on. What happens in this area? Well, if we get a mean over here, what are we doing? We're failing to reject, because we're going to think we're residing in this distribution with a mean of 100. We're failing to reject a false null, because again, the assumption here is the mean is 105. Again, if we get something over here, we're going to fail to reject the claim of 100 when we should reject. Again, probably pretty clear. Probability of a type 2. Now, in the next video, what I'm going to do is I'm actually going to fill these values in. With numbers. All right, so this is alpha, right? We already know what it is. But what would beta, 1 minus beta, and so on, what would those probabilities be? So we'll do that in the next video. All right, take care.